Hello everyone, myself Janvi, and today I'm going to prepare an audio recording for visually impaired students on the topic hard and soft acids and bases from Pradeep's Inorganic Chemistry Volume 3 by Dr. K. Bhasin. So let's start. Hard and soft acids and bases. The terms acids and bases are routinely used in our daily life. Chemists have been classifying substances as acids and bases since long time. Lavoisier noted the common element in all acids was oxygen. The word oxygen in Greek means acid former. However, Humphrey Davy showed later that all acids contain hydrogen. It was in 1884 Arrhenius, a Swedish chemist, developed the theory of acids and bases, known today popularly as Arrhenius theory of acids and bases. According to Arrhenius, an acid is a substance which gives hydrogen ions H positive in aqueous solution, and a base is a substance which gives hydroxyl ions OH negative in aqueous solution. The strength of an acid and a base depends upon its capacity to provide H positive and OH negative ions respectively. The process of neutralization of an acid by a base can be represented by the reaction H positive plus OH negative in equilibrium with H2O. In 1923, J. N. Bronsted in Denmark and T. M. Lowry in Great Britain independently proposed a new acid-base theory. According to their theory, an acid is a proton donor, whereas a base is a proton acceptor. The acid-base reaction, that is, the neutralization, is regarded as a proton transfer reaction. In 1923, J. N. Lewis gave another general definition of acid-base behavior in terms of electron pair donation and acceptance. However, this theory got the recognition only in 1938. According to Lewis, an acid is a substance which can accept a pair of electrons, while a base is a substance which can donate a pair of electrons. In other words, an acid is an electron pair acceptor, while a base is an electron pair donor. The earlier definitions of acids and bases were solely based upon the observable properties such as taste, ability to dissolve substances insoluble in water, and their effect on vegetable dyes. The term acid was applied to substances that have a sharp or sour taste, turn blue litmus red, react with certain metals to liberate hydrogen gas, and have the ability to dissolve substances insoluble in water. On the other hand, the term base was applied to substances that have a bitter taste, soapy feel, turns red litmus blue. However, tasting and feeling chemicals are dangerous methods for determining whether the substance is an acid or a base. You should never ever taste or touch solutions of chemicals in laboratory. There are, however, other methods of recognizing acids and bases. For example, acids and bases change the color of certain dyes, known popularly as indicators. One of the most common indicators is a vegetable dye obtained from lichen known as litmus. Aqueous solutions of acids turn the litmus red, whereas aqueous solution of bases turns it blue. Thus, any substance which has an unshared pair of electrons can act as a Lewis base, whereas a substance which has an empty orbital to accommodate a pair of electrons act as Lewis acid. In other words, substances capable of donating a pair of electrons are regarded as Lewis bases, and substances capable of accepting a pair of electrons are regarded as Lewis acids. Acid-base or neutralization reactions may thus be regarded as donor, Lewis base acceptor, Lewis acid reactions or coordinate covalent bond formation reactions. The classical example of a Lewis acid base reaction is that of between boron trifluoride and ammonia. Using electron dot diagram, we can see that boron trifluoride is the Lewis acid and ammonia is the Lewis base. NH3 plus BF3 react to give NH3 BF3. NH3 is the Lewis base, BF3 is the Lewis acid, and it gives donor acceptor or coordinate bond formation reaction. Lewis concept of acids and bases is very commonly used because of its simplicity and the ease with which the formation of coordination compounds can be explained. In brief, all the usual ligands can be regarded as Lewis bases, whereas all the metal ions can be regarded as Lewis acids. The degree of affinity of a metal ion for ligands can be termed as Lewis acidity, and the tendency of the ligand to combine with the metal ion can be regarded as Lewis basicity. Article 4.1 Hard and soft acids and bases. An acid-base reaction, according to Lewis concept, involves the reaction between a donor, for example A, and a base B, as to form a complex as given below. A plus B gives AB. The formation of the stable complex between the donor and the acceptor depend upon the nature of the species A and B involved. It has been known since long that certain ligands form more stable complexes with metal ions such as Ag positive, Ag2 positive, Pd2 positive, and Pt2 positive. On the other hand, certain ligands form stable complexes with metal ions such as Al3 positive, CO3 positive, and Pt4 positive. Based upon the preferential bonding, the acids and bases have been classified into two groups, with class A and class B according to their preference. Class A metal ions include alkali metals, alkaline earth metals, lighter and more highly charged ions, for example, Ti4 positive, Cr3 positive, Al3 positive, Fe3 positive, CO3 positive, etc. Hydrogen ion H positive. Class B metal ions include heavier transition metals of second and third transition series with cadmium 2 positive, mercury 2 positive, Pd2 positive, platinum 2 positive. Heavier transition metals in lower oxidation state which Ag positive, Hg2 2 positive, Cu positive. Low valent metal ions such as zero valent metals in metal carbonyls. Depending upon the type of ions, ligand can also be classified as class A or class B depending upon their preference. Class A ligands include molecules or ions with donor atoms nitrogen, oxygen, fluorine, chlorine, etc. It is important to note that class A ligands prefer to form strong complexes with class A metals. Class B ligands include molecules or ions with donor atoms phosphorus, arsenic, sulfur, selenium, iodine, etc. Class B prefer to form complexes with class B metal ions. It was in 1963 Pearson coined the term hard and soft acids and bases for class A and class B metal ions and ligands, respectively. Accordingly, class A metal ions are referred to hard acids while class B metal ions are called soft acids. Similarly, class A ligands are named as hard bases whereas class B ligands are termed as soft bases. In summary, According to Pearson, class A acids are hard acids. H positive, Li positive, Na positive, beryllium 2 positive, magnesium 2 positive, chromium 3 positive, iron 3 positive, etc. Class B acids are soft acids. uh, Gold positive, lead 2 positive, Cu positive, platinum 2 positive, etc. Class A bases are hard bases: H2O, NH3, fluorine negative, ROH, etc. Class B bases are soft bases: R3P, R3AS, R2S, R2SE, I negative, SCN negative, etc. 4.2 Article: Classification of acids and bases as hard and soft. Pearson observed that it is possible to correlate acid-base interactions on the basis of hard and soft acids and bases. He observed that type A metal ions, that is, acids, were small, compact, and not very polarizable, and these preferred ligands, that is, bases, that were also small and less polarizable. He called these acids and bases as hard. On the other hand, type 2b metal ions and the ligands they prefer appear to be larger in size and more polarizable. He described these acids and bases as soft. Pearson generalized the acid-base relationship and expressed that hard acids prefer hard bases and soft acids prefer soft bases. Classification of acids. A general classification of some common hard and soft acids along with some borderline cases is given in Table 4.1. Table 4.1. Classification of Lewis acids as hard and soft acids. Hard acids: H positive, Li positive, Na positive, K positive, beryllium 2 positive, magnesium 2 positive, calcium 2 positive, strontium 2 positive, aluminium 3 positive, scandium 3 positive, gallium 3 positive, indium 3 positive, La 3 positive, Cr3 positive, etc. Soft acids include Cu2 positive, Ag positive, Au positive, Hg positive, platinum 2 positive, cadmium 2 positive, mercury 2 positive, platinum 4 positive, etc. And metal atoms CH2 carbenes. Borderline acids include iron 2 positive, cobalt 2 positive, nickel 2 positive, copper 2 positive, zinc 2 positive, etc. An inspection of Table 4.1 reveals that hard acids usually have the following characteristics. First, hard acids are cations of smaller size or lighter elements. Second, hard acids are cations of higher oxidation states. For example, Cl3 positive, Cl7 positive, I5 positive, and I7 positive. Third, hard acids are molecules or cations with lesser number of valence electrons. Fourth, hard acids hold the valence electrons tightly and consequently are not easily polarizable. In summary, hard acids bind strongly to a proton. Hard acids are small size, compact, and are not easily polarized. A close look at Table 4.1 also reveals that soft acids possesses the following characteristics. First, soft acids are cations of the larger size or heavier elements. Second, soft acids are cations of lower charge. Third, soft acids are molecules or ions with large number of valence electrons. Fourth, soft acids do not hold the valence electrons tightly and are therefore easily polarizable. In summary, soft acids are large sized and easily polarizable ions, molecules that bind strongly to highly polarizable ion or molecule. It is important to note that there is no sharp division between hard and soft acids. There are a number of Lewis acids that are either neither too hard nor too soft acids. Such types of acids that are neither hard nor soft are called borderline acids, which are shown on the extreme right of table 4.1. Borderline acids have properties which are intermediate between that of the hard acid or and a hard base. In case of borderline acids, the properties such size, oxidation state, and polarizability of the cation or molecule are neither too low nor too high. On the other hand, soft acids will show the opposite trend, and the following order of preference for binding the donor atoms or ions with a group is observed. I negative greater than Br negative, greater than Cl negative, greater than F negative. R2Te greater than R2 selenium, greater than R2 sulfur, greater than R2 oxygen. R3Sb is greater than R3As, greater than R3 phosphorus, greater than R3 nitrogen. The above trend can be pictorially represented as complex of type A metal ligands, complex of type B metals, weakest to strongest. Ligands R3N, R2O, F negative, R3P, R2S, Cl negative, R3As, R2Se, Br negative, R3Sb, R2Te, I negative, weakest to strongest. Question 4.1. What type of interaction do you expect between a hard acid and a hard base? Since both hard acids and hard bases are not easily polarizable, their interactions are predominantly ionic. Question 4.2. What type of interaction do you expect between a soft acid and a soft base? Since both soft acid and the soft base are usually polarizable, the interaction between them are predominantly covalent. Classification of bases. A general classification of some commonly used ligands, that is Lewis base, into hard and soft bases along with the borderline bases is presented in table 4.2. A glance at the table 4.2 reveals that some of the important characteristics of hard bases are: first, hard bases bind strongly to the proton. Second, hard bases contain donor atoms of high electronegativity. Third, the donor atoms in hard bases possess low polarizability. Fourth, the hard bases are not easily oxidized. Fifth, hard bases contain empty orbitals of high energy. In summary, hard bases bind strongly to a proton. The donor atoms in case of hard base is of high electronegativity and of low polarizability. A further inspection of table 4.2 reveals that the following features are observed in case of soft bases. First, soft bases contain donor atoms of low electronegativity. Second, soft acids contain donor atoms of higher polarizability. Third, soft bases get easily oxidized. Fourth, soft bases are associated with empty low-lying energy orbitals. In brief, soft bases contain less electronegative non-metals, including carbon, sulfur, phosphorus, and iodine. The donor atoms in such bases possess donor atoms that are easily polarized. Such as there are borderline acids, there are borderline bases also. The properties of borderline bases are in between those of the soft and hard bases. It is important to note that the categories are not rigidly divided. For example, the halide ions form a series from the very hard fluoride ion through the hard borderline chloride ion to the borderline bromide ion and the soft iodide ion. The soft acids are also known as class B metal ions, are the group of metal ions that are in the lower right portion of the metallic elements as shown in figure 4.1. Article 4.3, Pearson's HSAB principle. Pearson proposed a simple rule for predicting the stability of coordination compounds formed between acids and bases. This rule is quite often named as HSAB principle. According to Pearson's HSAB principle, hard acids prefer to bond with hard bases, while soft acids prefer to bond with soft bases.